NASA's mighty James Webb Space Telescope has no shortage of accomplishments to its credit from its vantage point in space, roughly 1.5 million kilometers away from Earth. James Webb has been snapping breathtaking images and generating insights about stars, planets, and galaxies that were simply not possible by its predecessors. Glory follows glory. The premier observatory continues to lift the veil on the universe's history, revealing the secrets of 200 galaxies formed in the early days of the universe, some of which are as far as 10 billion light-years away from Earth. Join us as we dig deep into how Webb unlocks the secret of hundreds of galaxies at the edge of our universe. For hundreds of thousands of years, humanity has peered up at the night sky with one question top of mind: what else is out there? There's the moon, of course, and then the sun. And as our view of the night sky has come into sharper focus, we've discovered other objects too, like the 7 other planets that orbit the sun and their many moons. We've spotted comets, asteroids, black holes, and galaxies packed full of millions of stars. On especially dark nights, you can even spot the edges of our own Milky Way galaxy. So, exactly how many galaxies are out there? Current estimates suggest there may be as many as 2 trillion, that's trillion with a T-E, galaxies in the observable universe. Each galaxy has its own unique set of features and characteristics. Over the course of millions of years, they form gases, dust, stars, planets, and moons. At the center of most galaxies lies a supermassive black hole, which tugs at nearby stars. Famed astronomer Edwin Hubble became the first to devise a galactic classification system for celestial features in 1926. According to his very simplified classification, there are 5 main types of galaxies: spiral, barred spiral, lenticular, elliptical, and irregular. Only in recent years have we been able to estimate and understand how much else there is in the universe. Scientists use telescopes like the Earth-orbiting Hubble Space Telescope, Chandra X-ray Observatory, and the European Southern Observatory's Earth-based Very Large Telescope to carry out galactic surveys and identify how many galaxies are in a patch of the sky the size of a pinhead held at arm's length. Counting galaxies is kind of like playing a cosmic game of Where's Waldo. Astronomers are tasked with counting every galaxy they can find within that tiny sliver of space and then extrapolating it out across the entire sky. Carving a fraction out of the sky and identifying all of the galaxies in it across the broad spectrum of wavelengths is not an easy task. You have to fight through dust and other matter that may dampen a galaxy's light, and it takes a long time for Hubble and other telescopes to take these images and stitch them together. There are undoubtedly galaxies that we can't even see because our universe is expanding. Some extremely distant and old galaxies, which formed shortly after the Big Bang, are zooming away from us faster than the speed of light. It's virtually impossible to spot them with current technology. We largely have the Hubble Space Telescope to thank for illuminating our place in the universe. When it isn't chasing comets or counting planetary rings, Hubble periodically snaps detailed pictures of tiny slices of the sky. Hubble released the first deep field survey in 1995. We were trying to find sort of an indiscriminate area of the sky where no observation had been made before, Robert Williams, the former director of the Space Telescope Science Institute, told Vox in 2016. The image revolutionized astronomy. From the glittering image, astronomers spotted about 1,500 glittering galaxies. Subsequent images revealed even more. In 2012, Hubble's Stream Deep Field image was released. Over the course of 10 years, the telescope had snapped images of a tiny patch of sky for a total of 50 days. It revealed a slice of sky about 132 millionths of the sky, to be exact, scattered with twinkling galaxies of all shapes and sizes. Using this new image, astronomers estimated that there may be 100 to 200 billion galaxies in the observable universe. But just 4 years later, a team of researchers from the University of Nottingham reanalyzed Hubble's images and assessed data from other observatories, pulling our universe-wide galaxy count up by a factor of 10 to 2 trillion. The astronomers published their new numbers in the Astrophysical Journal. As astrophysicist Christopher Consolis of the University of Nottingham in the United Kingdom told The Atlantic at the time, it boggles the mind that over 90% of the galaxies in the observable universe have yet to be studied. Who knows what interesting properties we will find when we discover these galaxies with future generations of telescopes. In a sense, we're playing a game of cat and mouse with the universe. We're scrambling to develop instruments powerful enough to catch sight of galaxies that are zipping away from us at breakneck speeds. And as a result of a global effort, the James Webb Space Telescope was built to take Hubble's place as the preeminent galaxy-spotting space telescope. But it performed even better than predicted, far exceeding anyone's expectations. On July 11, 2022, history was made as the very first science image of James Webb was unveiled to the world. Upon its release, it immediately broke the cosmic record for the deepest view ever taken of the universe, a remarkable feat prior to Webb's first science release. The deepest view of our cosmos came from the Hubble Extreme Deep Field, a region of space so small it takes up just 132 millionths of the sky. Within it, 5,500 galaxies were found spanning almost the entire history of the universe, from just 400 million years after the Big Bang until today, or from when the universe was merely 3% of its current age all the way to its present state. That image represented the deepest view of the universe for a full decade. But by simply using its suite of instruments to observe a run-of-the-mill galaxy cluster, the James Webb Space Telescope has shown us the universe as we've never seen it before. The very first image taken by the James Webb Space Telescope, called Webb's First Deep Field, centered on a cluster of galaxies named SMX 0723 and containing no less than 7,000 galaxies. Just with this image, we all know that James Webb outperforms Hubble by more than we expected. Our newest space telescope could do much more in less time. Whereas Hubble has a primary mirror that's 2.4 meters across, James Webb's segmented mirror spans 6.5 meters. This leads to a resolution that's 270% as sharp for the same wavelength light and light-gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see above in the comparison of its composite image of galaxy cluster SMX 0723 with that of Hubble, is doing even better than that. Hubble's time is divided up into orbits, as from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 9.6 hours or 576 minutes of Hubble time. But there is only a total of 3.4 hours or 203 minutes of Hubble data that's gone into these images, despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 12.5 hours and got 12.5 hours worth of data. What's the difference? Well, location in space is extremely critical. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere in the way of its desired target and can only acquire useful data when its target is in full unobstructed view of the telescope. Meanwhile, James Webb is some 1.5 million kilometers away at the L2 Lagrange point. It always faces away from the Sun, away from the Earth, and away from the Moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency will extend to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. As you can see both above and below, there are plenty of regions of space that appeared blank to Hubble's eyes that are rich in objects when examined with James Webb. Yes, they remain underdense regions of space, but they're not empty the way some had either hoped or feared. Not only can James Webb find these objects, in many cases, it can resolve them and examine their properties, whereas Hubble could not even see them at all. This is going to help us achieve one of Webb's main science goals, to teach us, in the goriest details possible, how the universe around us grew up and came to be the way it is today. Most recently, in a remarkable revelation, scientists stated that the telescope continues to uncover secrets about the universe's history by revealing distances of nearly 200 deep space galaxies. This study was conducted by a team of Canadian and international astronomers led by Dr. G. Nutt, a postdoctoral researcher at St. Mary's University in Halifax. It's the first study to measure galactic distances in Webb's first deep field, showing huge collections of stars as far as 10 billion light-years away from Earth. Members of the Canadian Nearest Unbiased Cluster Survey, or CUNCS, the scientists used the Canadian Nearest or Near-Infrared Imager and slitless spectrograph instrument on board James Webb to collect spectra from galaxy targets in the image. These spectra are a type of scientific data created by breaking down the light of an object to reveal additional information, such as the object's age or distance. Using James Webb's near-infrared spectrograph instrument, the team measured the redshifts of nearly 200 galaxies whose distances from Earth were previously unknown. According to Nutt, the study's lead author, NEARES is perfect for doing this because it can measure the redshifts of hundreds of galaxies at once. The study will be a valuable resource for the astronomical community and open up new avenues of research. Added Nutt, from this redshift catalog, the researchers have uncovered many new galaxies in the SMX 0723 cluster whose light has taken more than 4 billion years to reach us. Clusters, which are huge groups of galaxies held together by the force of gravity, can contain up to thousands of galaxies. The new study brings better understanding of how galaxies evolve in some of the most extreme environments in the universe and gives a glimpse into the distribution of dark matter and the evolution of structures. As the National Research Council's Chris Willett, who leads the Canadian Space Agency-funded CUNCS team, said, as members of a Canadian-led project, we are even more excited that this significant improvement compared to previous studies of SMX 0723 was enabled by the spectroscopic capabilities of the Canadian-made instrument NEARES on board James Webb. This Canada-made technology is letting us use the James Webb Space Telescope to its fullest potential, added Université de Montréal professor René Doyen, director of the Trayer Institute for Research on Exoplanets and principal investigator behind the NEARES instrument. Within their huge collection of galaxy redshifts, the researchers identified 3 other galaxy overdensities at much greater distances than SMX 0723 that had not been seen previously in this field. These galaxy overdensities are potentially newly discovered galaxy clusters located 8 to 10 billion light-years away. Capturing these galaxy overdensities at different cosmic times is like watching a time-lapse movie of these clusters' growth from their infancy in a young universe to the present day. The clusters represent ideal targets for future studies to better understand how galaxies and the clusters they inhabit have evolved from their state in the very early universe to what they look like today, including our own galaxy, the Milky Way. Already, the CUNCS team has made an amazing find within one of these clusters, the magnificent Sparkler galaxy discovered in September 2022. It's a highly magnified galaxy some 9 billion light-years away, bursting with what appears to be the oldest star clusters to have formed after the Big Bang. What the team's new NEARES redshift catalog now reveals is that the Sparkler is not an isolated galaxy but resides in one of the newly discovered galaxy overdensities. According to SAI, a co-author of the earlier study, the fact that the Sparkler does not live alone but is a member of a family of galaxies has important implications for how first star clusters formed after the Big Bang. The CUNCS astronomers will be able to improve upon their galaxy redshift catalog during Webb's second year of scientific operations, now underway. As they have been granted time to reobserve Webb's first deep field in even greater detail with the NEARES instrument. The astronomy community clearly recognizes the value of our first NEARES redshift catalog and wants us to do another even better version, says Nutt, the principal investigator of this observation program. Several independent teams of scientists have used the catalog and the results of the new study to pursue their work on Webb's first deep field, and additional research stemming from the CUNCS advances is expected into the formation of galaxies, the distribution of dark matter, and the evolution of the universe. While James Webb continues to lengthen its list of achievements, the first-ever asteroid encounter of NASA's Lucy mission came with a twist. On Wednesday, Lucy zoomed past Dinky Nesh, a small space rock that resides in the main asteroid belt between Mars and Jupiter. Actually, Lucy zoomed past 2 space rocks, for the probe found that Dinky Nesh, whose name means marvelous in the Amharic language, is actually part of a binary system. The discovery added another layer of excitement to an already historic encounter. As Keith Knoll, Lucy project scientist from NASA's Goddard spaceflight,